Vector quantization index systems provide approximate nearest neighbor search through learned codebooks. This document describes the construction and operational parameters of the VQ codec subsystem. The index maintains a set of centroid vectors in Euclidean space. During construction, input vectors are partitioned into clusters. Each cluster is represented by a single centroid point. The assignment of vectors to clusters minimizes total distortion. The codebook is initialized through random selection or k-means, ++ initialization. The initialization mode is specified by the init strategy parameter. Valid values are random, k-means plus, and seeded. K-means plus is the default and provides faster convergence. The init strategy parameter must be set before codebook construction. Once construction begins, the initialization strategy cannot be changed without rebuilding the entire codebook. Codebook size determines the number of centroids and affects both compression and search accuracy. Supported codebook sizes are powers of 2 from 256 to 65,536. Larger codebooks provide better reconstruction fidelity but require more memory and longer query times. The codebook size parameter defaults to 1024. This size is suitable for high-dimensional spaces with millions of data points. Modifications to codebook size require complete index reconstruction. Vector dimension must be consistent across all input vectors. The system supports dimensions from 4 to 2048. Most applications use dimensions between 64 and 512. The dimension parameter is immutable after index creation. Attempting to insert vectors with mismatched dimensions returns an error code dimension mismatch. The system performs no automatic dimension reduction or padding. The iterative refinement process executes multiple passes through the training data. Each iteration reassigns vectors to nearest centroids and recomputes centroid positions. The max iterations parameter specifies the maximum number of refinement passes. Valid range is 1 to 100. Default value is 10. Most convergence occurs within 5 iterations. Increasing max iterations beyond 15 provides minimal quality improvement for standard workloads. Convergence criteria determine when iterative refinement terminates early. The convergence threshold parameter specifies the minimum change in total distortion between consecutive iterations. Valid range is 0.0 to 1.0. Default value is 0.0001. When the distortion change falls below this threshold, refinement stops. Setting this parameter to 0.0 disables early termination. The system always terminates at max iterations regardless of convergence state. Distance computation uses Euclidean distance by default. Alternative metrics are L1 Manhattan and cosine similarity. The distance metric parameter accepts values Euclidean, L1, and cosine. Euclidean distance is recommended for most general-purpose applications. L1 distance is more robust to outliers. Cosine similarity is suitable for normalized vector spaces. Distance metric selection affects both construction time and query accuracy. Cluster assignment uses hard assignment by default. Soft assignment methods are available through the assignment mode parameter. Valid values are hard, soft Gaussian, and soft exponential. Hard assignment assigns each vector to exactly one cluster. Soft assignment produces fractional memberships. Soft Gaussian assigns membership based on Gaussian distance kernels. Soft assignment increases construction time by 40 to 60%. Random seed initialization influences centroid positioning and convergence behavior. The random seed parameter accepts integer values from 0 to 2,147,483,647. Default value is determined by system clock. Specifying an explicit random seed enables reproducible codebook construction. Different seeds produce slightly different codebooks with similar quality. Reproducibility is useful for testing and validation, but not required for production use. Centroid update equations compute new cluster centers based on current assignments. For hard assignment, centroids are computed as the mean of assigned vectors. For soft assignment, centroids are weighted by membership values. All centroid coordinates are stored as double precision floating point values. Update computation is performed in batch mode for all clusters simultaneously. The system maintains update statistics for monitoring convergence. Empty cluster handling prevents cluster degeneracy during iterative refinement. A cluster is considered empty when no vectors are assigned to it. The empty cluster strategy parameter specifies recovery behavior. Valid values are reinitialize, merge, and preserve. Reinitialize selects a random unused vector as the new centroid. Merge combines the empty cluster with the nearest non-empty cluster. Preserve leaves the cluster unchanged. Pruning removes outlier vectors from training to improve centroid quality. The pruning strategy parameter controls outlier removal behavior. Valid values are none, distance-based, and density-based. None disables pruning. Distance-based removes vectors that exceed a distance threshold. Density-based removes vectors in sparse regions. The pruning threshold parameter specifies the percentile of vectors retained. Default value is 0.95. Query processing uses the learned codebook to find approximate nearest neighbors. Each input query vector is assigned to the nearest centroid. All vectors assigned to that centroid become candidates for the search result. The number of returned vectors is controlled by the K parameter. Additional candidates may be included from neighboring clusters. Accuracy improves with increasing K at the cost of query latency. Query speed depends on index size and cluster population distribution. Queries return results in order of distance from the input vector. The search radius parameter optionally limits results to a maximum distance. Setting search radius to 0 disables distance filtering. Candidate reordering occurs through post-processing using exact distances. Large codebooks with unbalanced clusters may exhibit variable query performance. Memory usage includes storage for the codebook and any cached cluster assignments. Codebook memory grows linearly with cluster count and vector dimension. Cached assignments require storage proportional to training data size. The memory mode parameter specifies storage strategy. Valid values are dense, sparse, and streaming. Dense caches all assignments. Sparse stores only outlier assignments. Streaming recomputes assignments at query time. Serialization stores the learned codebook for later use. The serialized format includes all centroid vectors and construction metadata. Serialized indexes are portable across compatible systems. Format version information is included for compatibility checking. Deserialization validates checksum integrity before loading. The system supports both human-readable and binary formats. Binary format requires 60% less storage than text representation.